histogram is a bar chart of a frequency distribution. Of a frequency distribution. Okay, so if I were going to have a histogram of the height of trees in a field, then what would I do? I'd go around, I have a big square plot of land. I go and I have maybe 100 trees or something in it, and I go and I measure the height of all of those trees. Now I could give you that list of information. I could give you a listing of 100 or 200 trees. That would be useful, but it would be more useful to create a frequency distribution, which we've already talked about, which is a tabular arrangement of classes and then the number of trees that fit into each of those buckets. So we could do that in tabular form, but perhaps even better is if we could represent it in graphical form, and we call that a histogram. So it's just a bar chart of the frequency distribution that we've already talked about in the previous section. So for instance, we would create something that looks like this. So we'd have, our two lines right here, and this would be the height in feet of the tree. You could use meters or whatever, it doesn't matter, but in this case we're going to use feet. And this will be the frequency, which would be the number of trees there. And I have to have some kind of scale here, so I have 2, 4, 6, 8, 10. And I'll label it 2, 4, 6, 8, 10. Okay, so let's say that between 60 and 65, right, I got something like 3 trees I measured being in this range, okay? And between 65 and let's say 70, I had 4 trees, so that would be that. Between 70 and 75, I had, let's say, 8 trees, straight up to 8, straight over, straight down, and this is supposed to be right at 75. And then going on from 75 to 80, let's say I had 5. So here's between 4 and 6 is 5, so this is about 5 right here. And then from 80 to 85, let's see here, something like that. 80 to 85, let's say it's something like, down here. And then from 85 to 90, it's just like 1 tree. Because it's pretty rare to have a tree that tall. Okay, so this is a histogram, all right? So it is representing the height of the trees in the field, but it's not graphing every single height of every single tree. It's graphing these buckets that we've talked about before. Couple of things to know about histograms. They're a graphical way to represent that information. We can quickly look at, in this range right here, we have so many trees that are that high. In this range right here, we have 8 trees that are that high. So we can see at a glance what is actually the highest frequency of all of our data, which would be in this case, this guy right here. A couple of other things. In a histogram, the bars, right? The bars do touch in a histogram. Remember I told you that in a bar chart we talked about, typically the bars don't actually touch. There's a gap there. But in a histogram, they do touch. And the reason is because the boundaries here, see these are class boundaries, the boundary here is shared among the 2 adjacent classes here. So of course they're going to touch, and that's what they do touch. The widths of the classes here, they're uniform. It's not like you have some of them that are wider and some of them that are narrower, and we talked about that before, and so on. So typically that's how you're going to draw a histogram. It's a graphical way of representing what we already know, which is a frequency distribution. Now you can also draw something called a relative frequency histogram, which you might guess is exactly the same thing, except we're graphing the relative frequency. So in this case, the heights show the relative frequency, which can be useful because we talked about the concept of relative frequency. So for instance, if we had the age of kids that learn to walk, right, that learn to walk, then we might construct a histogram that might look something like this. And let's say we're going to do it in terms of a frequency, relative frequency histogram. So we'll just draw our two lines like this. This is the number of months of age the child is. And then we have to have something up here. So let's say, because this is a relative frequency histogram, it's going to be percentages. So this is going to be 10%. This is going to be 20, 30, and 40. So 20%, 30%, and 40%. Remember, we talked about histograms. We talked about relative frequency, which is just basically taking the frequency of your class, dividing by the sum of all the frequencies, and that gives you a percentage when you multiply by 100. That's what we're basically graphing here. So if I were going to do this, then I would say, let's say between the ages of 6 and 8, I get something like 10%. And when I say 6 and 8, it's 6 and 8 months of age. Very rare for a kid to learn how to walk that young, so that's why the bar is so low. But between the ages of 8 and 10 months, it jumps up significantly up to 30%. So here we have 30% like this between that guy there. Now between 10 and 12 months of age, it's really, really high, up here around 40%. Most kids are probably going to learn how to walk somewhere around the 1-year mark. And then between the ages of 12 and 14 months, it goes down, but not quite so much. Let's say 20% of the kids learn to walk there. So we can see quickly, because this histogram is graphed in terms of relative frequency, which is just percentages, what we can quickly see is that, okay, between the ages of 10 and 12, 40% of everybody that we looked at is actually, learning to walk in that age. But a close runner-up is here, and then not too far behind is here, but way out here, obviously not very common for that to happen. So it's kind of just representing the same information. We didn't have to use relative frequency, but sometimes you do, and so I'm trying to teach you that by examples there, was what it might look like. So for the last part of this lesson, let's go ahead and construct a histogram by hand. So let's go ahead and look at our raw data. This would be, let's say we're doing a study and we're looking at the breaking time for cars in minutes. Now you know what I mean, right? When they test cars, they have a test driver, and they go down the course, they slam on the brakes. Some cars are going to stop in a really short period of time, which is really good. You want that. Some cars, if they're heavy or if the brakes don't work right or who knows why, they might take a much longer time to brake. So the time that it takes for the car to stop after you slam on the brakes, that's what we're measuring right here. And we're measuring that time in terms of minutes, right? We could measure it in seconds, but in this particular case, the data is given to us in minutes. So we would have a class, right? And we're going to have some frequency. Right? So let's go ahead and write this stuff down and see what we get. So for the class 0.05 minutes to 0.07 minutes, we get 12 cars that stop in that region. From the class 0.08 to 0.10, we have 15 people, or 15 cars, that are able to stop there. Then we have 0.11 to 0.13, we have 14, and then we have 0.14 to 0.16, we have 15, and then we have 0.17 to 0.19, we have 14. So basically in this particular chart, the smaller the time, the better it is. That's the kind of car you want. If you can afford a car that stops really, really, really quickly like this, one of these 12 cars, that's what I'd want to buy. But who knows what kind of car that is. It might be a really small car. It may not be big enough for your family. It might be, who knows. That may be a car that catches on fire really easily or something. So, but this is the raw data for braking. Now what we want to do is construct a histogram, right? So what we would typically do is we would draw our two lines, right? And then we would say this is the braking time in minutes. That's the braking time in minutes. But here's where you got to be careful, and this is why we're doing this problem. A lot of students, when they do this, are going to take the class endpoints like this, and they're going to take them and they're going to put them down here, and then they're going to graph their histogram. That's going to produce a histogram that looks about right, all right? But technically, you're not supposed to use these numbers right here because look here, 0.5 to 0.7, 0.8 to 0.10, 0.11 to 0.13. You see how there's no overlap in these classes here? That's on purpose, but the problem is if we draw it on the graph like them, then we're going to have a gap between the adjacent classes, and we already said that for histograms, the bars really should touch. Everything should be sandwiched together, but notice from 0.07 to 0.08, there's a gap there. So if we actually use these numbers to write our bars down, it's not going to quite look right. So what you need to do is you need to find the class boundaries. And the class boundary is actually what you put down here, and that's going to make it touch. That's a very simple little concept, but that's right. Now let me ask you this. What would be between 0.07 and 0.08? Because the class boundaries are exactly halfway between the endpoints there of the adjacent classes. So 0.07 and 0.08, you're going to get 0.075 on this side. And over here, what would be, if it's 0.075, what would it be on the other side? It would be 0.045. Now what would it be here? Would be on this side and on this side, halfway between. Well, first of all, since this is 0.075, we know this is going to be down here. What would be halfway between 0.10 and 0.11, basically? You're going to get 0.105, okay? 0.105. So then you're going to carry this down here, 0.105, and then what would be halfway between 0.13 and 0.14? It's going to be 0.135. So then you carry this down, 135. What would be halfway between 0.16 and 0.17? 165, right? So then you carry this down, 165. Because this is going to be on the left-hand side of this guy here. What's between, well, there's no further classes. So since you know that you're just going halfway between everything, you can see the pattern and see that this one's going to be 0.195. So these are going to be the classes. You're going to have these class boundaries here. When you write your histogram, you typically want to use the class boundaries. Mostly because histograms, you want to see everything sandwiched together with no gaps between your bars. So you need to find the class boundaries, which are basically the midpoints between the adjacent classes. That's what you're doing. So really what we're doing when we look between 0.13 and 0.14, we know that it's 0.135, but really we're averaging 0.13 and 0.14. You know, we're adding this plus this, we're dividing by 2, which gives us 0.135 there. So for this particular case, it's a little bit easier. All right, so here's our histogram. And let's just draw some stuff here. We'll go, this is 11, 12, 13, 14, 15, 13, 14, 15, something like this. And then for our classes, now on the bottom we have to use the class boundaries. So what we have is 0.045. And this one, just to make it kind of easier to read, I'm going to write it down here, 0.075. So in this class, between these class boundaries, I have 12 cars that actually break there. So I'm going to write that like that. Now, from 0.075 to 0.105, so here I'm going to have 105, and I have 15 cars right there. So it pops up, lots and lots of cars seem to break right there, like that, and so that's what we're going to do. And then from 0.105 to 0.135, I'm just making these longer so that I can stretch the numbers out so they don't run into each other. I'm going to have 14. 14 is here, so that goes something like this. From here to here, 0.165, I have a frequency of 15. 15 is way back up at the top again. And then finally, 0.165 to 0.195, I have 14 people, which goes back down to here. That would be my histogram. All right, that would be my histogram. So as I said before, the frequencies, they're graphed exactly the same way. You just kind of use a bar chart. You want the bars to touch. The way you make them touch is you use whatever class limits you have to find the class boundaries. You're just looking at the midpoint between the classes like that, and you're going and you're creating kind of a new window where the end of one of these guys becomes the beginning of the next one, typically is how you want to do that. And that's done whenever you're graphing your histograms. Now, if you have a calculator, like a Texas Instruments calculator or some other fancy calculator, when you put your classes in, it's going to take care of a lot of this stuff for you. What we're doing now is we're kind of learning the nuts and bolts behind it. If you use a computer program or a calculator and you put that data in and you assign the classes, it's going to create that graph for you with the appropriate boundaries here. But notice all of the widths of these rectangles are all the same, and they're all touching. The widths don't have variability there because that would make for an ugly histogram. You don't want one skyscraper to be a different width than the other one. You want everything to be a uniform width so that I can easily compare the height of these different classes as we run down the line. Histograms are important. They're very, very important. So make sure you understand how this works. Make sure you understand the general topic. That's why we introduce frequency distributions first, because that's kind of the underlying thing, and then we apply it to bar graph, basically. We call it a new name called a histogram. So make sure you understand this, then follow me on to the next section where we're going to learn something called the stem and leaf diagram, which is just another way to represent raw data in statistics. Learn anything at mathandscience.com.